So for this last video for 6.1, we're now going to get into the evidence we have nowadays for evolution. So we have talked about the common misconceptions and arguments against evolution and dismantled all of those. We looked at some of the history behind evolution as a concept with Charles Darwin, and now we're going to look at modern times and the evidence that we use today to solidify evolution as a theory. And the first piece of evidence is the fossil record. The fossil record shows the progression of life's development throughout millennia, right? Through the years and years, millions and millions of years. Now, it's important to note fossils are the preserved hard parts. So it's really hard to find fossils in general, and it's even harder to find fossils that are of soft organisms. Typically, when we think fossils, we're thinking bones, teeth, and shells. One of the cool things though about fossils is that because of different radioactive isotopes, we can determine the fossil's age using radiometric dating, also known as carbon dating. You don't have to use carbon, you can use other atoms depending on how ancient you're trying to go, but some people will probably be familiar with the term carbon dating. But we can determine how old a fossil is based off of the certain isotopes that we see for things like carbon. And so using this ability to age or date fossils and put them basically in some sort of chronological order, we can create a record that creates what we call evolutionary trees, which will show the relationships between species and their common ancestors, and can include what we would call transitional fossils. So transitional fossils are fossils that share characteristics from two major groups. The one that I'm going to talk about today is Tiktaalik. However, there are many, many different examples. Tiktaalik is a very famous transitional fossil that was found within my lifetime. And Tiktaalik is an organism that shares characteristics of both fish and amphibians. So you think fish, you think fins, you think the eyes are on the side of the head, you think no neck, you think scales, you think gills and underwater, right? And when you think amphibian, you think the eyes are in the front of the head. We have lost our scales and now have more of like a slimy skin. We can go on land. We have limbs instead of fins. We have a neck. So we've made some major changes, right? And we look at fish and amphibians, there doesn't seem to be much overlap. And with Tiktaalik, we see an organism that has scales like a fish, that has fins, but has shoulders like an amphibian, whose eyes are in the front of their head like an amphibian, and had the ability to push itself up. Right? This is basically a fish in a way that knew how to do a push-up and could push itself up onto land. So we saw that Tiktaalik had traits of both major groups, both of fish and amphibians, leading us to say that this is one of those organisms that transitioned us from water to land. So let's look at the radiometric dating. How do we even know what order these fossils go in? Besides where they're found in the rock layers, which can also help, we use radiometric dating. Radiometric dating relies on the use of radioactive isotopes. Radioactive isotopes are elements that basically break down into stable compounds at a very constant rate. So we can measure basically how much is broken down and know the rate of that breakdown. So what we see here is if we have this radioactive isotope within this rock, right, it's 100% this radioactive isotope, which is very unstable. Over time, the radioactive isotope will break down into something much more stable, right? We move from unstable to stable, but it does so at a very particular pace. And so we see from 4.5 billion years ago, we had 100% radioactive isotope. Today, it's now half gone, and so half of it's stable, half of it's radioactive for that isotope. And if we continue down the line 4.5 billion years from now, we would see we're down to 25%. 9 billion, we'd be down to 12.5%, right? Then to like 6.25%, so on and so forth. So it's getting cut in half, right? In this case, our unit of cutting it in half is 4.5 billion years. So every 4.5 billion years, the amount of the radioactive isotope gets cut in half. Again, you can use radioactive carbon, nitrogen, phosphorus. There's a whole bunch of them that can be used for radiometric dating depending on how far back you're looking roughly. So in this case, we're looking at uranium-238. The half-life is 4.5 billion years. And this is what we've used to determine how old the Earth is. So like we wouldn't use carbon because that's not really useful, but something like uranium-238, we know that the half-life is 4.5 billion years. And so we can use that to determine, okay, all the uranium-238 was this radioactive isotope 4.6 billion years ago, and now we have half of the amount, roughly half the amount we would expect from the original amount. I won't get into the nitty-gritty, again, of radiometric dating, just because that's getting more into like chemistry and physics. But do keep it in mind, this is a tool that we use that is very reliable when it comes to determining the age of things. And so here we see Tiktaalik. So we look at Tiktaalik and we look at the animal itself. This is obviously an artist depiction based off of the fossil that we found and fossils that we found. And we see that it looks kind of in between. It has scales like a fish. It had gills. It had fins. But it had arm-like joints, so it had a shoulder. It could push its body upward. The eyes moved from the side of the head to the front of the skull. Right? So we've seen these major changes, and so it looks kind of like a mishmash, like a hodgepodge of fish and amphibians. Going into our next piece of evidence is biogeography. So the example we're using is the Hawaiian honey creeper. These guys are adapted to a wide range of habitats, and yet they still look like an ancestor found nearly 2,000 miles away. And so what we've seen with these guys is that depending on the environment, we see certain types of changes. So for the Akeke, I think I'm pronouncing that right. Akeke honey creeper, they live in wet forests at higher elevations, and so they're eating a lot of like bugs. So they have a beak that would be decent for that. The Maui parrotbill honey creeper lives at an even higher elevation and eats insects, but we're looking more at like larvae, and so it has something that can maybe dig those larvae out. And then the iiwi honey creeper is living at even higher elevations, and its diet is nectar from flowers. And so you see how this beak is better suited for getting nectar out of a flower versus like getting insects like spiders. And so the idea is that these guys, a finch-like ancestor, got from mainland North America to Hawaii about 4 to 5 million years ago. So geographical location can be a distinct predictor in the characteristics we see, and biogeography is our second piece of evidence, looking at the study of distribution patterns of living organisms. What we see is that species are more similar to local species in different habitats than they are to distant species in similar habitats. So that tells us that basically organisms moved around a long, long time ago. So like when we look back here, we see that Hawaii is a pretty far distance off from North America, but close enough that you could have some travel, right? The environments are very, very different. Hawaii is very much more tropical, whereas North America is more temperate. So they're close enough to be able to move around, but the environments are different. Versus if you look at Hawaii versus maybe a tropical area on the other side of the planet, that other tropical area in Hawaii might be very similar in terms of environment, but we don't see similarities the same way in the organisms there because there's not as close of an evolutionary relationship. There's not a common ancestor necessarily between those two, at least not a more recent one. And so the reason that we see this, the reason that species are more similar to a local species, even though the habitat might be different, compared to distant species in similar habitats is because evolution doesn't lead to the same, quote, solutions just because the habitats are similar. Yes, sometimes this happens, and we'll talk about that in a little bit, but it doesn't always. It depends on what traits are already present in the organisms facing that problem. So if there are similar traits, you might see similar solutions, but just because the environmental pressures are the same doesn't mean you get the same outcome, because you have to look at what traits you are even starting with in the first place. So let's go ahead and look at a good example of what we would call convergent evolution, where we look at the Australian marsupials and their placental counterparts. Marsupials are pretty much found on Australia exclusively, and placental counterparts, placental mammals, would be pretty much all other mammals. And what we see is that there are similar solutions, but not necessarily the same. So like the sugar glider in Australia is a marsupial that has this like stretchy band of skin it uses to glide. And like in North America, the flying squirrel is placental. It has something similar, but when the big differences between these guys that is much larger than any flap of skin is how they have their offspring. And the same thing for the numbat and the giant anteater, the Tasmanian wolf, now extinct, and the gray wolf. Next, we get into the comparative anatomy and embryology, which is our third piece of evidence supporting evolution and showing the similar origins between organisms. When we look at vertebrate embryos in the very early stages, we see that all of these embryos share what we call gill pouches and a tail at some point in their development. The gill pouches and tail may disappear later, but every embryo has these structures at some point, including humans. And so we would call this a homologous structure, where the structure is similar but the functions end up being different down the line, suggesting that there is a common ancestor. A good example of homologous structures is looking at the forelimbs of vertebrates, of mammals. So if we look at like the forearm of a person, so your arm, versus the front paw of a cat, we see that the structures are very similar in that you have the same basic bone structure of one bone in the upper arm, two bones in the forearm, and then many bones making up the wrists, the hand, and the digits. And no matter which one you're looking at, whether it's the cat or the human, you see that same pattern of one, two, and many. The difference is the functions. We use our arms for grasping and carrying things, whereas a cat will use theirs for locomotion, for moving around. But because the basic structure is similar across the board there, we can say that there's a common ancestor who had some sort of front limb similar to both of ours. There's also sometimes evolutionary leftovers called vestigial structures, and we can find these in modern day organisms, including humans. The most common or most famous vestigial structure are the hip bones found in whales. Whales do not have back legs, and yet they do have rudimentary hips. Snakes are in the same boat, where they also have these rudimentary hips. And for example, with humans, things like our wisdom teeth would be considered vestigial as well, and also our tailbone is another one. So there's a lot of structures that are considered vestigial because they are basically shrunken, not really useful structures that are basically ghosts of traits past. So before the modern day whale came to be, there was an ancestral version of a whale that did have back legs. And when we look at humans with the tailbone, we have this tailbone that is super teeny tiny, small little fused bones that is reminiscent of somewhat of a tail. It doesn't serve as a tail in us anymore, but at some point in time, our ancestors to humans did have a tail. So we see that it's basically a shrinking, disappearing trait that still has some remnants left, right? It's in the process of being completely phased out. But we never really truly 100% phase all of these vestigial traits out because there's no evolutionary pressure to remove that structure, right? There's nothing harmful about a whale having rudimentary hip bones, and so there's no pressure to make sure those hip bones completely disappear ever. It's basically a no harm, no foul kind of structure in that it doesn't do anything. It's basically now useless at this time, but it also doesn't do any sort of harm, so it doesn't have any pressure to be filtered out of the organism, basically. So let's go ahead and look at those homologous structures I was talking about earlier, where I talked about the forelimbs. Now, I mentioned a human and a cat because I'm a cat lady, but for the example here, we have a human arm, the horse's front limb, a bat wing, and a porpoise fin. And so what we see, even though on the exterior, all of these limbs look different, right? We have an arm, a front leg, a wing, and a fin. We see the basic structures underneath have the same pattern. One bone in the upper arm, two bones in the forearm, many bones making up the wrist, and then the digits. And we see that here. One bone, two bones that fused together, that you can see kind of a distinct line there. Many bones, digits. One bone, two bones, many bones, digits. One bone, two bones, many bones, digits. And what mainly has changed here is not necessarily the pattern, but the shape of the bones. They've been stretched longer and thinner. They've been squashed shorter and more squared off. We've maybe added a couple more bones in, like in the digits here versus in the digits of like the human fingers. We maybe changed their shape and modified them a bit, but the basic pattern is there. And the basic patterning there tells us that there is a common ancestor that all of these organisms, the human, the horse, the bat, and the porpoise, all share. Now, earlier I mentioned that sometimes you do see similar traits pop up in seemingly unrelated organisms. And we call this convergent evolution, where it produces some different structures that have different starting materials, but you get similar results. So a good example of convergent evolution would be something like the wings of a bird and the wings of a bee. Both of the structures are used for the same function, flying. However, if you look at the structure of a bird wing and a bee wing, you see that they're totally different. Think about the bird and you have bones and muscles and skin and feathers, and in the bee you have more of like a membranous, thin, translucent wing. So structurally, they really share nothing in common. The only thing they share in common is the function, the purpose for those structures, which is to fly. So basically, the birds and the bees were both put under the same pressure in that they needed to get off the ground. They needed to be able to take to the skies. But the starting materials to allow for that trait of flight to appear were totally different. It's kind of like if I told you to build a house and I was going to build a house, but I gave you bricks and I used wood. Or you would then have to build your house out of bricks. I would have to build my house out of wood because our starting materials are different. At the end, we would both have houses. They would both serve as shelters, but the building structure, the building materials are different. When we look at closely related species too, we also see that genetically they're more similar than the more distantly related species. Even though all known organisms use the same genetic code of DNA to mRNA to protein, we see that genetically we can look for basically the changes that have happened. And when we look at more closely related species, there are fewer changes compared to distantly related species where there are more changes. And there are a lot of experiments that have basically shown this in action. We can directly observe the results of these changes. A really good example is antibiotic resistance. Now, we didn't watch this in class today because this is an asynchronous course, but what you will be watching is a video, if you haven't already, is a video on antibiotic resistance for your discussion. Antibiotic resistance is a problem we are facing today and is a direct result of evolution in action, in that we are using antibiotics to cure us of illnesses that are bacterial, and bacteria are responding to that by developing traits or populations, I should say, of bacteria are developing traits that allow them to survive even in the presence of antibiotics. A good example of what antibiotic resistance is leading to is MRSA, or methicillin-resistant Staphylococcus aureus. Staphylococcus aureus is a common bacteria found all over the place, and generally can make us ill, but generally not too bad, and is cured by antibiotics. Methicillin-resistant Staphylococcus aureus, or MRSA for short, MRSA is resistant to the medications, the antibiotics we use to cure us of Staphylococcus aureus infections. So we've seen a change, and MRSA is just one of several. We're seeing it with the MRSA. We're seeing this with things like chlamydia and gonorrhea, the aptly named super gonorrhea. But basically, like, we're seeing bacteria go through evolution, go through natural selection because of the antibiotics that we use. But let's get into those homologous structures, looking at the embryo stage and relating all of the vertebrates together. So several slides ago, we looked at gill pouches and the tail. And we said that no matter what you were, including humans, if you were a vertebrate, meaning you have a backbone, then you had gill pouches and a bony tail at some point in your time, in your life. And we see that here. So in orange are the gill pouches. So here's in the shark, the turtle, the human, and the chicken. And then the bony tails in green here, in the shark and the turtle here, the human, and the chicken. So we see that at some point in all of these organisms' lives, they had both of these structures. Now, they do become different things in organisms later. So like in the shark, the gill pouches do give rise to the actual gills. In humans, it becomes parts of our inner ear and our throat. So we've modified what we use this early embryonic structure for, but the structure is there nonetheless, showing that we basically took things and modified traits to give us new traits or seemingly new traits, rather than trying to reinvent the wheel, creating a new pathway, a novel trait out of nothing. It's a lot easier to use something as a starting point and transform it than it is to come up with something brand new, never before seen from scratch. One of the last things we're going to look at is hemoglobin, the genetic similarities there as well, showing us kind of those evolutionary relationships. Hemoglobin is an important protein that helps us transport oxygen around in our blood. And there is a gene that codes for a certain polypeptide that helps build hemoglobin, because hemoglobin is made of 4 different chains. And so we're looking at the beta chain of hemoglobin. When we look at one human compared to the next, they're all the same. All 146 amino acids making up the hemoglobin chain are the same. When we look at a rhesus monkey, which on this list is our closest relative, not our actual fully closest relative, but the closest one on the table here, we see that 138 of those amino acids are the same and 8 of them are different. We look at the dog, we now have 114 that are the same, 32 that are different. The bird, 101 are the same, 45 are different. And then we get all the way back to the lamprey, which is pretty much almost as far human as you can get while still looking at animals. We see that 125 of the amino acids are different and only 21 are the same. And we see what we're using here, what we're kind of figuring out from here, is that it's hard to accumulate this many changes. It takes a lot of time. And so the more changes you see, the longer or the further back that common ancestor is. So we're not saying that after 8 changes we went from rhesus monkey to human. That's not what we're saying. We're saying that there was a common ancestor shared between the rhesus monkey and the human, and that over time the rhesus monkey line and the human line diverged at 8 of those amino acids. And that took 23 million years to happen. We go back to the dog, we see that in order to accumulate those 32 amino acid changes, it took 46 million years. and with the bird, 112 million years. And with the lamprey, 564 million years. So basically what we're saying is that change is slow for the most part from one species to the next. And that we're not saying we came from an already existing species. We're saying that these are the number of changes that have added up since we had a common ancestor.